All right, so now that we have the hydroxylation taken care of, let's take a look at what can happen after you hydroxylate. So P450 is going to take this CH bond and turn it into a COH bond, and then we're going to have a chemical step. Okay, the chemical step is whereby the oxygen pushes its electrons, and you kick out X. Okay, X in this case is going to be our leaving group. The reason why this is a pretty favorable chemical step and doesn't require any sort of enzyme is because when you collapse down with the oxygen's electrons, you can deprotonate it, and when you deprotonate it, the final product is going to be neutral. Okay, it's going to be neutral, and that's pretty good. Now, the identity of X is what determines what reaction we're dealing with. If X equals OR, it's O dealkylation. You got an oxygen, you have an alkyl group, O dealkylation. If it's NR2, where there's a nitrogen and an alkyl group, it's N dealkylation. Works via the exact same mechanism, it's just different names for the same type of reaction. If there's no alkyl group attached to the nitrogen, basically you're dealing with an amine, it's oxidative deamination. And then if you have an S with an alkyl group, it's S dealkylation. Okay. If there's a halogen, okay, you kick out a halogen, either Cl or Br, that's oxidative dehalogenation. Okay. So in terms of terminology, if there's a alkyl group attached to like our oxygen or a nitrogen or whatever, then it's an dealkylation. If there's no alkyl group attached, it's like deamination or dehalogenation, and then you just give the prefix of oxidative. Now, the ones that I think you really should pay attention to are the N dealkylation and the oxidative deamination. They are the same reaction. They work the exact same way. It's just kicking out an NR2 leaving group versus an NH2 leaving group. The reason why you want to pay attention to them is because you're going to end up with this tetrahedral intermediate where you have an OH, you have an NR2 or an NH2. And the thing is, nitrogen is not as electronegative as oxygen. So what can happen is these electrons can push and generate a double bond, and then you can kick out the OH. You can kick out the OH as a leaving group, okay? And the resulting intermediate that you're going to get is R with a C double bonded to the nitrogen, and then R double prime, okay? This is not that stable, but if you form this intermediate, it's susceptible to nucleophilic attack, okay? So it's susceptible to nucleophilic attack right here, right? If DNA attacks, it'll be carcinogenic. If a protein attacks, it could generate an immune response. Basically, that's not good. Okay, this reaction is reversible, however, because you have a positive charge on the nitrogen, can't really deprotonate it, and it's just going to reverse back to the tetrahedral intermediate. And then this tetrahedral intermediate, you can follow the normal pathway to get the ketone or the COO bond by kicking out the nitrogen group. Okay, so there we have it. Elimination followed by hydroxylation. It's basically just all these dealkylations or deamination reactions. You basically hydroxylate using P450 followed by a chemical step.